We're going to look at a problem having to do with resistance and resistivity and electrical measurements you would make to determine resistance and resistivity. The problem we're going to consider deals with soil, and it's actually going to deal with a kind of a clay soil. We don't have clay soil, but we do have Play-Doh, and it turns out the resistivity of Play-Doh is actually comparable to that of some clay soils. And it's not a huge surprise. They're actually reasonably similar in terms of how they're made up. So I've got a chunk of Play-Doh here, and there's a cylinder of it. And if I have two electrodes here, I have a positive electrode and a negative electrode. They're connected to a power supply. And if I connect the positive electrode to the Play-Doh and the negative electrode to the Play-Doh, I can measure the current through the Play-Doh. And right when I connect it, it's making a current of about 100 milliamps, right when the current goes to the Play-Doh. So 12-volt power supply, and I'm getting a current of about 100 milliamps through here. Now that'll allow us to determine things about the Play-Doh. It'll allow us to determine things about it. Because if I know the voltage and know the current, I can compute the resistance, but the resistance is a property of the dimensions, the length, the diameter, and also the resistivity, which is a property of the material. It's the resistivity which someone measuring soil would be interested in, because the resistivity is a clue to what's happening in the soil, specifically how much moisture is there and how much dissolved salts are there. Let's take a look at the problem. You can measure the moisture content of soil by measuring its resistivity. A researcher has taken a core sample of clay soil and is measuring the properties of a cylindrical section that is 15 centimeters long and 5 centimeters in diameter. When he applies a 12-volt potential difference between the ends, he measures a current of 100 milliamps. What is the resistivity of the soil? If he repeats the measurement on a sample with the same diameter but twice the length, what current will be measured? Well, let's do some preparation. And by preparing, we're going to go ahead and we're going to locate some of the important variables in the problem and just kind of wrap our mind around what's happening here. So we are measuring the resistivity of a sample of soil. And it's cylindrical, and it's 15 centimeters long, and it's 5 centimeters in diameter. And we hook that chunk of material up in a circuit, putting a 12-volt potential difference across it and measuring a current of 100 milliamps. Now let's start by thinking about this question. We're going to be looking for resistivity. To be able to measure resistivity, we have to know resistance. And with the data that's given, what is the resistance of the chunk of soil? We'll give you some choices. And of course, you know how to do this. This is a basic circuit problem. We take a little power supply, we hook it up to a resistor, which in this case is a chunk of soil. And if I have a potential difference of delta V and a resistance of delta R, we're going to get a current that goes through the circuit. And the resistance that's happening here, the resistance is just equal to delta V divided by I. Well, the voltage is 12 volts. The current is 0.10 amps, and so we end up with the resistance of 120 ohms. So that's the resistance of the sample. But we're not looking for the resistance, we're looking for the resistivity. So we need to know, what is the relationship between resistance and resistivity? And when I say we, I mean you. So I want you to tell me, what is the relationship between resistance and resistivity? We'll give you some choices. Well, the relationship between resistance and resistivity looks like this. The resistance is equal to rho times L divided by A. The resistance is the property of the specific chunk of soil. The resistivity depends, it's just a material property. The resistance also depends upon the dimensions of this particular cylindrical chunk of soil. So now let's continue. And before we're ready to solve, let's do some additional preparation. I'm going to rewrite my equation, R is equal to rho times L over A, and say the resistivity is equal to R times A divided by L. And in order to be able to calculate the resistivity, I'm going to have to calculate the area. Because we're given the length, this chunk of soil, okay, we're told that it has a length of 15 centimeters. Okay, and we need to put that in meters, so it's got a length of 0.15 meters. A is the cross-section area through which the current flows, because we're passing current through it like so. The cross-section area is just the area of the end, and the area of the end is just equal to pi r squared. We're assuming it's a cylinder, so it's got a circle as the end. Well, the radius of the circle, it's 1/2 of the 5 centimeter diameter. We need to put it in meters, so it's 0.025 meters. With that in hand, we calculate the area as 0.0020 square meters. Okay, so we know the area, we know the length, and with that in hand, we are ready to solve. And what we're solving for the resistivity, and we have everything that we need because the resistivity is just equal to the resistance, which we've determined, times the cross-section area divided by the length, and we have all those values here. We know the resistance, we know the cross-section area, and we know the length. So if I take all those numbers and I put those numbers in, I get a resistivity of 1.6 ohms times meters. Okay? So that's the solution for the resistivity, but we're not done yet because the next part of the problem asks this. What would happen if you repeat the measurement on a sample with the same diameter with twice the length? How would that change the current? Now that's a problem that you can solve just by doing ratios. You don't have to do another calculation. You can just work that one out by thinking about how the variables in the basic relationship change. I want you to take a moment to do just that. What do you get for the new current? We'll give you some choices. Now let's rewrite our basic relationship for current. Okay, current is equal to delta V divided by R. And R is the resistance of the sample, but the resistance of the sample depends upon the resistivity and the dimensions. Okay, so the resistance depends upon the resistivity, the length, and the area. Now the area stays the same, the resistivity stays the same. That's a material property. The length goes up by a factor of 2. He's looking with a sample that's twice as long. So what that means is the resistance goes up by a factor of 2. Well, if the resistance goes up by a factor of 2, the denominator of this expression goes up by a factor of 2, which means the current is going to decrease by a factor of 2. And so what that means is instead of having 100 milliamps of current in this second case, it's just going to be 50 milliamps of current. And there's only one piece that's left. We've calculated the resistivity, we've calculated the new current. Now we want to step back and take a quick assessment and see if our results make sense. The numbers that we got from the soil were comparable to what we got from Play-Doh, and the number that we come up with for the resistivity for the soil is something you can look up, and it's actually comparable to values which you would find for resistivity of clay soils, which is comparable to the resistivity of Play-Doh. So that makes some sense. So our answer seems grounded in reality. But let's also look at the second part of the problem. The second part of the problem asked, if we took a sample of soil that was twice as long but had the same diameter, what current would be measured? Well, we measured one piece of soil, we got 100 milliamps. If we had two connected together, I'd end up with a sample that's twice as long. But electrically, what this looks like is this piece right here and this piece right here. Of course, they're just connected in series. And so we'd expect, hooking them up to the power supply, measuring the current, we'd get a current of about half what we measured before. And in fact, that's exactly what we get. It's not a surprise. Physics is about the world around us.